Okay. Hopefully, you have seen my email. Just to emphasize on what we have already discussed in class and what was in the email, your exam 2 has moved to April. What date was? April 19th, right, which is a Monday. I'm pretty sure. So the Monday before the classes end, the Monday before the last lecture. And the graduate presentations have moved to April 26th, which was supposed to be the exam date. Your exam 2 will only focus on chapters 4 and 5 and a little bit of flight mechanics that we are going to talk about in class. And so this means that exam 2 is going to be in 2 weeks, exactly 2 weeks. Okay. We are at the final stretches of this semester, so hopefully you will all get a very good grade out of this course. You will all get an A. And you will have a better experience on exam 2 than you did on exam 1. Okay. And your homework is due Wednesday, right? I think so. Is it due today or Wednesday? Today. Okay. Homework is due today. So I will post the next homework on Wednesday, which will be due. This is the last homework, right? Which will be due the following Wednesday. So in 10 days, right? And again, I may not be able to come in for Wednesday's class because this is in anticipation of me getting my second shot of the vaccine, right? Usually people fall ill for a day. I'm taking it on Tuesday, so I may not be able to come in on Wednesday, right? I will try to record a lecture just to be prepared. And also there was an audio problem during the last lecture. So online students couldn't watch the lecture completely. I will try to re-record those part of the lecture and upload it online. Is there any questions? No. So homework will be posted on Wednesday. It will be due the Wednesday after this Wednesday. And so in 10 days, your exam will be in exactly 14 days, 2 weeks. Will be chapters 4 and 5. We will have at least one exam review session. So probably what I'm going to do is do a total of 2 exams. We will finish this chapter by this Wednesday, hopefully. So next week, we will do the first part of a class review on Monday, which is mostly focused on the final exam, whatever you need from the first 2 chapters for the final exam. Then we will do another exam review on Wednesday, which will focus on chapters 4 and 5 for your second exam. And I guess that's it, right? Let's start the class. Let's start the lecture. And let's actually start with an attendance quiz again. And I want you to tell me what are, or let me change the question. Is there going to be any changes to angle of attack? Any changes to angle of attack due to downwash phenomena? And this is the angle of attack. Is there any changes to angle of attack due to downwash phenomena? And this is the local angle of attack that your wing sees, right? So the idea here, again, just to refresh your memory, let's say this is your wing. The idea here is that whenever you are dealing with a three-dimensional wings, instead of two-dimensional wings, three-dimensional effects come into play, right? We have a very high pressure region here, also here, and very low pressure here, region here. Whenever you have a high pressure region and low pressure region, you will definitely see a flow happening there, right? That's the idea. That's the basic principle of fluid flowing, right? Fluid flows from a high pressure region to a low pressure region, right? It is essentially the same as like pushing your flow, right, in one direction. So we will have some movement in this direction, and this is, to be a little exact, this is what it looks like. Okay, I will continue. So what's going to happen after this downwash effect is that here, specifically at the tip, there won't be any pressure difference between the lower surface and the upper surface, meaning that there is no lift at the wing, right? At the wing tip. So the question is, and this is something we discussed in the previous lecture, the question is, what will happen to the effective angle of attack, to the angle of attack that your wing sees, right? Is this a clear question? Is it going to be an acceptable answer? Is that nothing, right? Nothing will happen to that angle of attack. It may be a wrong answer, but it is acceptable. And we have the same deal as the previous attendance quiz. If you get it right, we get a bonus point. Okay. And I want you to think about it yourself. You don't need to go back to your notes or whatever. Just want to come up with a rational or logical explanation. The idea here is to get your minds going, right? Not to get a correct answer. To start up your minds. So I'm going to give you a couple of minutes to think about this, come up with a solution, come up with an answer, and we'll go from there. If you have any questions about the downwash effects, please make sure to ask. I will try to clarify this. If not, think about the possible changes to angle of attack or lack thereof. You can ask your colleagues' opinions. You can discuss this and see what is the conclusion you're making. Okay, I guess we have had enough time to think. Just send your papers, hand your papers, just pass your papers to the front. Yes.
I wrote it out.
Send an email to me. Yeah, send an email. Yeah, that's it. And thank you. Thank you. Okay. Okay, so let's see what is the answer to this question. To answer this question, you let me change this. You first have to know what is the angle of attack, right? The idea was the angle of attack is the angle between the flow direction, free stream flow, right? And the coordinate. That's the idea. So let's say you have fluid or air moving in this direction with a velocity v infinity, right? And you have your airfoil in this direction. Like that's the. What would be the angle of attack here? It is this angle, right? Alpha. Right? So let's think about it. What will happen to this direction of the flow on the wing? Right? When you have the downwash phenomena present, what will happen to that direction? Just one quick note, just to make sure you are not confused. This is a side view. And this is a front view. Okay. So what will be the velocity component that can be seen in this side view representation of the wing from downwash? You will see a component of velocity that is moving in this direction, right? Moving down. Let's call that W. And you have your velocity, regular velocity v infinity in this direction. So, pardon me? We have some velocity pushing the flow in this direction, right? And we are looking at it from the side, right? This is what I'm saying, right? Okay. Pardon me? It's not the weight? Weight. You mean weight? I'm not sure I'm clear. A weight of what?
The airfoil. It's not gravitational weight.
No, this is a small W. This is not gravitational. This is not a small W. No. Are we clear on what is this velocity component W? This is not weight, right? This is what we call the induced velocity. Okay, velocity that is induced by the downwash phenomena on the wing. Okay, what does it mean for the flow direction that your wing sees? Yeah, flow is going to be tilted this much, right? So your flow direction is going to be different. What does this mean for the angle of attack? this effectively means that angle of attack is going to be, the effective angle of attack that your wing sees is going to be different as well, because your flow direction is different, right? So your angle of attack is going to be this new one. Let me use a different color. This is going to be the what we call the local wind's direction. Okay. And the effective angle of attack is going to be the angle this makes with the chord length. So your angle of attack that your wing sees is going to be smaller than the geometric angle of attack, right? Does this make sense? So your effective angle of attack is going to be equal to your alpha, or geometric angle of attack, minus what we call an alpha I, which is this part. And this is called induced angle of attack. Okay? Is this clear? So what does this mean for the lift? Your lift is also going to be tilted, right? Because lift is the force normal to the direction of velocity. So if we didn't have the induced angle of attack, if there was no downrush phenomena, this would have been the direction of the lift, right? Because of the induced angle of attack, the lift, that for the normal force is actually tilted a little bit. And this projection of the lift force is called the induced drag. This is the reason actually we called all of these induced angle of attack, induced velocity, induced drag, because all of these are induced there by lift, right? We are losing some of the lift to the drag because of the tilt in the local wind direction. Okay? Does this make sense? Okay. So the purpose of this chapter in general is to find the value of induced drag, which effectively means that we want to find the value of lift, because the two are obviously, you can see from this thing, related, right? This induced drag is a projection of the lift, right, in one of the coordinates. The angle here is actually the induced angle of attack. And also finding the induced angle of attack here, and lift, and all of those things. That this is the purpose of this chapter. This is the purpose of the chapter 5. Three-dimensional analysis, wing analysis. We already know how to calculate lift in a two-dimensional analysis, but we don't know how to include the effects of downwash yet. Okay. Before moving on, let me ask you one question, one kind of a side question. Is this induced velocity going to change as we move from the wingtip to the wing root? From the wingtip to the wing root. So from this side, this part, this is the wingtip. To where the fuselage is, wing root. Yes. Okay. That is correct. Is this going to increase or decrease? It is going to decrease, right? Because the biggest flow is going to happen here, from here to here, right? And the flow is going to become less effective, less strong, or weaker as we move from the tip towards the root. When you have a weaker flow, yes?
I was thinking those two are going in different directions. So wouldn't they like cancel out? Oh wait, that makes sense.
Okay. So as we go from the tip to the root, this velocity is going to become smaller and smaller and smaller, and the effects of induced drag are going to become less dominant, right? Which means that we have to calculate, we have to have an equation that gives us the angle of attack or the induced drag or whatever as a function of the location on the wing. It is not going to be a constant value. Since this W changes, right, this angle is going to change as well, right? So this is something which means that it is going to be a little, the whole thing is going to be a little complicated. But before moving on, before doing all of the analysis over there, I'm finding the values for lift, induced drag, and the induced angle of attack. We want to talk about the drag coefficient. So drag coefficient based on this is a combination of your drag that is due to the shape of the wing, the roughness of the wing, all of those things, the viscosity, all of those things, which we are going to call residual drag, or a parasitic drag, depending on the type of analysis, but that's out of the scope of the course. Okay, plus the drag that is induced by lift. Induced by lift. Okay, two type of drag. And of course, finding that this drag coefficient, induced drag coefficient, follows the same type of analysis that we had before. Induced drag is going to be equal to induced drag coefficient is going to be equal to induced drag divided by Q infinity S. Right? That was the idea. That was the definition of the force coefficients. Okay. So let me ask you this one question. What will happen to the D'Alembert paradox here? If you don't remember what the D'Alembert paradox was, the D'Alembert paradox told us that if you neglect the effects of viscosity, you are not going to be able to calculate drag, right? Which is a paradox, it's an unphysical phenomenon, right? But what will happen to that D'Alembert paradox when you move from an infinite wing or a two-dimensional analysis to a finite wing, right? What do you think will happen to it? Think about it. Neglecting viscosity meant that we are going to get zero drag, right? So that was a two-dimensional case. What does neglecting viscosity mean for a three-dimensional case? Right? Which part of this drag, or is it all of it, is going to go to zero? So this goes to zero. This is what they're saying. the other one. You are correct. Joshua is correct here. So this part is the part we also see in the two-dimensional analysis, right? This is the drag by pressure. This is the viscous drag. All of those things are wave drag, whatever kind of drag you have that is due to the geometry that is going to change based on the geometry is included in this part, right? So the D'Alembert paradox applies to this part. But as long as you can calculate the lift, you should be able to calculate the induced drag, right? And removing, neglecting viscosity from our calculation didn't mean we are going to get zero lift. We were able to calculate lift. If you remember, we had the rotating cylinder, right? And we calculated the lift for it. So removing, neglecting viscosity doesn't mean we are not going to get induced drag. And as long as you have induced drag, you have a drag coefficient, which means that the D'Alembert paradox does not apply in the three-dimensional analysis. Okay, that was a sidetrack. That was a side note. But let's move back to the main point of the class. We actually don't want to move the boards anymore. Okay. How can we calculate this induced angle of attack and induced drag and all of those things? Okay. We want to go back to something that we also saw in the chapter 4, right? Vortex filaments, right? The idea was we can have a lot of these vortex filaments together over there. If you recall, vortex filaments went from negative infinity to positive infinity, and then we replaced a wing with all of a two-dimensional airfoil with all of these vortex filaments. We were able to calculate circulation and lift and all of those things. It's the same idea here, but with a couple of very important differences, right? So to refresh your memories, vortex filament, essentially, it's a line vortex that goes from negative infinity to positive infinity, right? And it has a circulation gamma, right? It has a constant circulation gamma. Okay. Can we use this type of analysis? Can we use this type of vortex filament when we are analyzing wings? Right? That's the first question you need to answer. And the answer is no. Why not? Because this vortex filament goes from negative infinity to positive infinity, but your wing doesn't go from negative infinity to positive infinity anymore, right? That was a two-dimensional airfoil case. In two-dimensional airfoil, the idea was it is an infinite wing, right? Negative infinity to positive. So we cannot necessarily use this vortex filament. So what should we do? We are going to generalize the idea of vortex filament. Instead of a linear vortex, we are going to talk about a curved vortex. Okay? Let's see how can we use the ideas of a curved vortex filament to analyze things. So we are going to make this more generalized. Curved vortex filament. Okay, so the only difference we have here was that this was a linear vortex filament. This is a curved vortex filament. Okay. The first thing we did when we were analyzing vortex filament was to find the velocity induced at the point P. Okay. By this vortex filament, by the very small section of this vortex filament. Let's call this instead of ds, we are going to call it dl here. Velocity induced by dl on P, which is going to be dv, right? Since we are dealing with a vortex filament, your equation is going to be a bit different, a bit more general. dv is going to be equal to a strength of your vortex dl cross r, and this is r, divided by all of these are vectors, all of by the magnitude divided by magnitude of r by 3. If you simplify this equation to a linear vortex filament, essentially a two-dimensional case, your dV would become gamma divided by 2 pi ds ds. So that was the idea, 2 pi r. That was the main difference here. So this is a special form of this general equation. And this equation is a very important equation in inviscid flow. This is actually based on a law called the Biot-Savart law. If you have passed any electronics physics course, you can see that this is very similar, it's essentially analogous to the magnetic field induced in medium surrounding a wire that has some current passing through it. Right? So dl is exactly the same equation divided by 4 pi. The only difference is that the strength of vortex over there is permeability of that medium multiplied by the current, which is analogous to the magnetic field. So we already know how to calculate velocity induced by a curved vortex filament. Is there any questions here? Just an equation, just a generalization of something we have seen before. Okay. And I don't want to wipe these parts. Let's actually deal with two special cases. One, the special case of a line vortex that goes from 0 infinity to infinity. This is your dl, goes to p. This is the projection of your r onto the vortex. Let's call this h. And the velocity induced here, we can calculate it to be total gamma divided by 2 pi h. Right? We have had this before. The only difference was h was r. Right? That was the only difference. And let me actually do this as well. If you have a vortex filament that goes from 0 to positive infinity, your velocity is going to be equal to gamma divided by 4 pi h. So this velocity is going to be half of this velocity. And there are two bonus points here. Use this equation and get to these two. Prove these, right? Proof of these equations already is in your lecture notes, also the books, also the book. You can find it in many other books as well. Okay, you get bonus points if you are able to calculate this. Okay, so let's keep these here. Velocity induced by a linear vortex filament is at a specific point P is the circulation, the strength of that vortex, right, divided by 2 pi multiplied by the distance, the closest distance between that point and your vortex filament. If your vortex filament is going from negative infinity to positive infinity, okay? And the other one, if your vortex filament goes from 0 to positive infinity, then your velocity can be calculated using gamma divided by 4 pi multiplied by the closest distance. Okay. So that's one thing that we are going to use in developing the theory, in the finding the equation that is going to give us the induced velocity and all of the variables we are looking for. The second thing is called the Helmholtz Theorem. Helmholtz Theorem. It has 2 points. The Helmholtz Theorem has 2 special points. First is the strength of the vortex filament cannot change. So gamma of a vortex filament is constant. The second one is a vortex filament cannot end in a fluid. Okay? So if you are in a fluid, your vortex filament has to go from negative infinity to positive infinity. Okay? Unless you're hitting a wall or something in that fluid. Okay. So we have this velocity. We have this Helmholtz theorem. Let's see how we can replace a wing with a vortex filament. Let's do this. What do you think? Let's say this is your wing. Downwash phenomena is present. Because of it, it is a wing, and velocity, air, is moving towards your wing. Okay. What do you think I should do? I want to replace this wing with a vortex filament. That's the idea, right? That's what we want to do. How should I do so? If I use a linear vortex filament that goes from negative infinity to positive infinity, I'm not representing this wing, right? If I go from this, let's start from 0 here. So we have b over 2, negative b over 2 to 2b over 2, right? And this is the center of the coordinate system. If I go from negative b over 2 to b over 2, I'm violating the Helmholtz theorem. So what should I do? How can I use this vortex filament to analyze a wing? Like this. So a couple of problems. Okay. One problem is that what should I do about it? So this one vortex filament cannot replace the whole flow over there, right? It is just one line, right? And if you do a vortex sheet, what is going to happen is that you cannot reproduce the type of flow, right? And also, again, you are going from negative infinity to positive infinity here, right? This has not changed the problem. So you are going to replace your wing with an infinite sheet, right? What else? Try to be a little creative. What kind of a change I can make to this vortex filaments? Think about it. What was the most general idea that we introduced here? I wrote it here, right? When it came to vortex filaments, that they can be curved, right? So have that that idea in your mind and see how you can apply that to this. What do you think?
Can you do like a U, like around the front of it, and onto both of the?
Like this?
Yeah.
Okay. Let's see if that works. So this is something you're thinking, right? It goes from negative infinity, right? Because we don't have a limit, to positive infinity, right? So it doesn't violate the Helmholtz theorem, right? And it's still a vortex filament. So why not? Exactly. That's the idea. Thank you. So we are going to bend the vortex filament that we are going to use. These type of vortex filaments are called horseshoe vortex filaments. Horseshoe, because they resemble a horseshoe, I guess. And this type of movement here is actually resembles your wing-tip vortices. Does this make sense? Do we all understand here? So we don't want to violate the Helmholtz theorem, but we still want to use a vortex filament here. And we already know that vortex filament can be curved, so we are going to bend the vortex filament. We're essentially going to use a vortex filament that looks like exactly, it is broken, right? We are going to break it to 3 different vortex filaments. Okay. So this is one vortex filament. How did we relate the vortex strength or the circulation to lift? Does anyone remember? What was the theory we used to relate lift to the strength of the vortex? Lift per unit span and strength of the vortex. It was the Kota-Joukowski theorem, right? What did it tell us? It told us that lift per unit span is equal to gamma rho v infinity, right? I think I'm missing one variable. Is it the chord length? No. Yeah. So rho v infinity gamma. Your circulation multiplied by rho and v infinity. Is rho changing here? No. Right? Is v infinity changing here? No. So if you replace all of the flow over a wing with one vortex filament, what are we going to get? We are going to get this type of lift distribution. And this one is a front view of a wing, right? Of the same wing. Since based on this theorem, the strength of that vortex is just 1. This is what you essentially are going to get as lift distribution. Lift as a function, L prime as a function of y, right? So lift at each point. Is this a correct representation? No. Why not? Exactly. Thank you. So the idea was, this is something we saw in the previous lecture as well. The idea was that because of the downwash phenomenon, lift, we already know, and this is something we have discussed, that lift is there because of the pressure difference between the lower surface and the upper surface of the wing, right? So if at these tips you don't have a pressure difference, right? If the pressure difference is the same, is 0 essentially pressure difference, your lift is going to be 0. So this will be the distribution of the lift. So what should we do to get from here to here? At least get closer. Let's do this. Let's add another vortex with a different, I'm going to put it like this. Let's use a different color. Another vortex with a different strength. Okay, let's say a higher strength. How would your lift be distributed here? It will be like a step thing, right? You're essentially adding the new circulation on top of your distribution, right? That's the idea. So what will happen if you add another one? Your lift is going to look like this. Okay? So what does this mean? That we have to have infinite number of these horseshoe vortex filaments, right? To be able to resemble the distribution of the lift on top of your wing. Is this clear? Yes? So we want this step thing to become more closer to this type of, be closer to this type of distribution, right? You have to add the vortex filament, the horseshoe vortex filament, and add millions of them, like to make sure that this looks like this. Okay. So that's the idea. That's what you want to do at the end of this. But let's go back to the one vortex filament and calculate the induced velocity due to that vortex filament. Let's do it here. And this is, let's have this. This is your vortex filament, right? We can divide this to three different sections, three different parts. Part 1, part 2, and part 3. Let's start with part 3. And the idea here is what we want to do. We want to find the velocity induced by this vortex filament on the wing. So the velocity induced by these three parts on this part of the vortex filament, on part 3. Is there any velocity induced on the wing, on this part, by the part 3? No, right? Why? Because this is the center of this vortex filament, of this part of it, right? It is not going to, this is not going to induce any velocity on itself. Okay? Does this make sense? Yes? I want to hear yes from everyone. Does this make sense? If it doesn't, you can ask your questions. If nothing does make sense, that's all right too. Just have to let me know. Does it make sense? Okay. We still have a couple of holdouts here that haven't responded. Does this make sense? Where's the question?
I was just kind of getting a little confused on like what the charts versus like when you have like the graphs and like they're stacking up.
Okay. Okay. So you understand this formula, right? Lift per unit span is a function of circulation, density, and V infinity. Is V infinity changing? No. Is density changing? No. So the only thing that can change here in an inviscid flow is circulation. Okay. So let's say we have replaced the wing with this vortex filament, this orange one, right? Let's start with that. And this is a kind of a top side view of the wing, right? But I want to have only a front view here, a front view of the wing, right? Circulation is constant, is a constant value. Let's say I want to plot, let's say this is y, this is your lift per unit span. Circulation is just a number, right? So how would that number change when you only have one vortex filament with a constant circulation? Is it going to change at all at different parts of the wing? Think about it here. Circulation on this part, this is one vortex filament. Circulation here is the same as here, as here, as here, as here. What does it mean for the lift? It will be constant. Then the question was, does this represent the distribution of lift on a wing? The answer was no. This is something we discussed in the previous class, right? The lift is distributed non-uniformly, if you will, because of the different pressure differences we have, right, at different locations. So how can we make this uniform distribution look more like a non-uniform distribution? It is basically an elliptical distribution, right? How can we do that? We're going to introduce another vortex filament at a different location, right, with a different strength, right? So here, if this lift is only generated by, let's call it gamma 1, right? At this location, gamma 2 starts up to this location. So your lift here is going to be gamma 1 plus gamma 2, right? Does this make sense? Then if you add a third one, it will be gamma 1 plus gamma 2 plus gamma 3. If you add an infinite one, it will essentially go from 0 to whatever gamma, right? Does it make sense? So the next step for us, as long as we understand this, the next step is to calculate the velocity induced on the wing, the W, this velocity, okay, induced on the wing by, we're going to start with one vortex filament, okay? We're going to start with only one. What is the velocity induced by one vortex filament on the wing? The idea here is that this part of the vortex filament doesn't induce any velocity on itself, okay? You may be confused by the analysis we had in the previous chapter, right? That we said this part of the wing induces a velocity here, right? This part of the airfoil. That was a different analysis. We were talking about many vortex filaments stacked beside each other that created a vortex sheet, right? So we had millions of vortex filaments. Here we only have one vortex filament, okay? So we are talking about only one of these that does not induce any velocity on itself. Does it make sense? Okay, so this part of the vortex filament does not induce any velocity on itself. What about these two parts? Are these going to induce any velocity here? On these points, no. They are not going to induce any velocities because these are the tip points, right? They are essentially part of these sections of the vortex filament as well, right? But what does this remind you of? This specific section of the vortex filament. Go back to your notes, or no, you don't need to go back to your. What does this remind you of? What does it? I'm pointing at it. What does this remind you of? A vortex filament that starts from 0, goes to infinity. This is the center of the coordinate system. This is one of the axes. So it starts from 0, goes to infinity. So we already know how to calculate the velocity induced on this line, on this wing, by this one vortex filament, right? That's gamma divided by 2 pi h. The only trick here is to find the h. Okay? Let's say you want to find the velocity induced by this vortex at this location. Why not, right? This is the center of the coordinate system. Goes from B2, negative B2 to B2, right? Instead of 0 to B, I'm putting the center here. We're going to put the center at the middle. go from negative b2 to b over 2, right? So what would be the velocity induced by this section? Is going to be the shortest distance, this distance, which is y0, minus this value, whatever this value is. So this distance, right? This is the distance. Is y0 minus this distance, right? This is going to represent h. So gamma divided by 4 pi, that's negative gamma, b over 2 plus y. And the velocity induced by this one is going to be in the other direction. Gamma divided by, that's why we have a negative sign, b over 2 minus y. Okay, just to make sure that we are not confused, this induced velocity would have been the velocity induced by this section, which was section 1, plus the velocity induced by this section, right? Velocity induced by this section 1, is gamma divided by 4 pi h, right? What is h here? Is negative b2 minus y, right? We have taken a negative sign out. And this is what we have. And here, the h here is going to be b2 minus y, whatever that is, right? Two different directions. Is this clear? No. Where is the question? Okay. So let's see. Let me actually clean this. This is your wing. Okay, and this is, let's only have one section of that vortex filament. This is the center of this is your y-axis essentially. And we only have one section of it. I want to find the velocity. This is x-action, I'm sorry. This is your y-axis. I want to find the velocity induced on this axis, right? On this location. Based on the analysis we already saw, and this is actually you are going to prove this as a bonus point. It is going to be the strength of this part, gamma, divided by 4 pi, multiplied by the shortest distance. What is the shortest distance? This distance, right? This is negative b over 2, 0, negative b over 2, minus this y, right? Okay? Let me take it. You do the same analysis for the other side, you get to that equation, right? Okay. And the thing is, the induced velocity is in a different direction, right? The velocity this induces is in this direction, right? Going down. The velocity this one induces is in the other direction. Okay? And you just have to do a negative sign. Yes.
Why did we just use the multiplier divided by 2 pi? Was it just maybe we're just multiplying by 2?
Would it be the same thing? So what you're saying is that if I don't do this analysis, if I combine these two, this is what I'm going to get. Right? Is it what you're saying? Okay, let's combine these two. Is this what you're getting, though? This is good. Your denominator is going to be 4 pi b squared over 4 minus y squared, right? That's the denominator. It's not the same thing. Why did we use it? Because we have two vortex filament, 2 parts of the vortex filament that go from 0 to infinity. We had to use it. We didn't choose to. This is the thing we had, right? Okay?
Wait, so wait, I'm just curious, the only question I have is why is p over 2 plus y versus p over 2?
That goes back to the location of the location on the vortex. That goes back to the distance. That's actually, if it's only your question, we can talk about it after the class, okay? Because we are running a little behind. Okay, so if you combine the two ratios, this is what you're going to get. Negative gamma over 4 pi multiplied by b over 2 squared minus log squared. This is the velocity induced by one vortex filament, right? But the idea here is that we want to replace this flow over wing with infinite numbers of vortex filaments. So what should we do? We have to find dW. Your dW is going to be equal to negative. I'm going to replace this with this, d omega, d gamma, dy, okay, multiplied by dy. How your circulation changes on the wing, right? Dy. That's right. I just want to make it a partial differential thing. And that's multiplied by 4 pi y naught minus y. So the circulation induced at y naught by the vortex that is located at location y. Essentially, if you look at this, let's say this is the location of your vortex filament, and this is the location of y naught on which you want to find the induced velocity. The distance between the two, that's the idea, okay? So we have dW. The only thing we need to do to find the induced velocity is to take the integral from one tip of the wing, negative b over 2, to the other tip of the wing, positive b over 2. Negative d gamma dy divided by y naught minus y. We can take the 1 over 4 pi out as well. So that will give you the induced velocity at location y naught. Is there any questions here? No. As long as you understand these parts, the rest of it is just mathematical game, right? You don't really need to understand how we did that game over there. It's not that hard to comprehend, right? Okay, so that's the induced velocity. If you have the distribution of circulation, you can find the induced velocity. But the next question is, how can we find induced angle of attack, right? Which is essentially the same angle here, alpha I. What is the relationship between induced velocity, W, and V infinity? We are going to use the tangent relationship, right? So you're going to get induced angle of attack is essentially tangent of negative y divided by the infinity. Since we are dealing with very small induced angle of attack, we can remove the tangent. So induced velocity is going to be equal to negative y naught divided by v infinity. Okay, so we already know how to calculate the induced velocity. Just have to plug in that equation here. So your induced angle of attack is going to be 1 over 4 pi v infinity, right? Integral b over 2 to b over 2 d gamma dy divided by y naught minus y. So induced angle of attack. Okay. So we already know how to calculate the induced velocity. We already know how to calculate induced angle of attack. The next part is, the next question we need to answer is how to calculate the induced drag, right? What is the relationship between drag, lift, and induced, you have a question? Induced angle of attack. Based on what you see here, what is the relationship between lift? Yes. Mm. That's, you answered your own question. It does, yeah. We had a negative sign inside, we have a negative here, right? That's just the directionality of it. So nothing important. Negative is already canceled out. Okay. So what is the relationship between the induced drag and the lift? Let's actually use this side. And the induced drag and the induced angle of attack. What is the relationship between d of I and alpha I and L? Take a look at this. Sine of your alpha I is equals to what? The induced drag divided by L, right? We are dealing with a small, very small induced angles of attack. So your alpha I is going to be equal to, we can remove the sign, di divided by L. Okay. As long as we have alpha I, we have di, and we have the L. As long as we have alpha I and we have L, we have di. We can calculate di. This is something we are going to come back to later. I don't think we have enough time for it today. But let's finish this part. Okay, so we have alpha I, and we want to calculate the effective angle of attack. The idea was your effective angle of attack is equals to your geometric angle of attack minus alpha I. So you either want to calculate the geometric angle of attack using the effective angle of attack and the induced angle of attack, or the other way around. Okay? How can we approach this problem? We have a lot of unknowns here. The only thing we really can calculate already here is your induced angle of attack. Okay? What are the other formulas that we have already seen that is going to help us calculate either the effective angle of attack and alpha? Go back to your chapter 4. what did we have that related your lift coefficient to 0 lift angle of attack and the angle of attack and also the lift slope? What was that equation we had? The idea was that, I guess I have to put in this part. The idea was that you have this CL versus alpha, right? Alpha L equals to 0, 0 lift angle, and this is what you have as a distribution. So your CL is going to be your lift slope, which was 2 pi multiplied by alpha minus alpha 0 lift, right? How did we get to this equation? Based on the definition of the slope of the linear part, right? Let's say this is the alpha you're looking for, and this is the CL. How did we calculate this slope? This slope 2 pi was equals to CL minus 0. That's the lift coefficient of the 0 lift angle of attack divided by alpha minus alpha L equals to 0, right? That was the idea. So we have this relationship between CL and alpha. Okay? I don't know if you should continue or should we leave the rest of it to the next lecture. Because we are out of time. Let's stop here. So we are going to start from this part, right? So let's say we finished here. We are going to start from the effective angle of attack. We will talk about the Prandtl's lifting line theory in the next lecture. We're going to start the flight mechanics part in the next lecture. And let's see, how many more lectures do we have? We have 3 more lectures, right? And then we have an exam and a presentations. So, okay. So we only have 1 lecture remaining, right? The other 2 should be exam reviews, right? Okay. Yeah, we'll finish the lecture. We'll finish this chapter in the next lecture. We moved a little slower than I anticipated. Okay, have a good day. See you all on Wednesday. And enjoy